All right, day 18. Today we're going to break down one of the most fundamental and, frankly, most useful ideas in all of machine learning, linear regression.
So picture this. You get a bunch of data, you plot it on a graph, and what you see is just a cloud of dots. It looks pretty random, right? Kind of like noise. The question is there a simple pattern hiding in there? And if there is, how would you even begin to find it?
By the end of this, you'll get it. You'll have the core intuition for how a machine tackles this exact problem. You'll see how to find that simple straight-line story that's often hiding in plain sight.
Okay, let's dive in. At its heart, linear regression is a tool for solving a prediction problem. Our job is to find a meaningful signal that's buried inside what looks like a bunch of random noise. And the solution starts with a really simple, almost beautiful idea. Instead of trying to connect every single dot perfectly, we just make an assumption. We assume that the relationship can be roughly captured by drawing a single straight line right through the middle of the data. That line, that becomes our predictive model.
And that right there is the essence of linear regression. It's a model that assumes a linear, or a straight-line relationship exists between your inputs, which we call features, and the single output you're trying to predict, which we call the label.
But of course, you could draw an infinite number of different straight lines through that cloud of points, which leads us to the most important question. How do we define what the best line is? How does a machine figure out which one to pick?
This brings us to the core mechanic of how the model learns. It finds the best line by systematically trying to minimize its own mistakes, or what we call its error.
The process is actually really intuitive. Just imagine we draw a line, any line, through our data. Then, for every single data point we have, we measure the vertical distance from that point down to our line. That distance, that's our error for that one single prediction.
Now, these little errors have a formal name. They're called residuals. A residual is just the gap between the actual value we observed and the value that our line predicted. So, the objective becomes crystal clear. The best fit line is the one that minimizes the total error when you add up the errors from all the data points. We just want the line that is, on average, the closest to everything. The most common method for doing this is called ordinary least squares. The key word here is squares. We don't just add up the errors. We square each one first, and then we add them up. Squaring does two really important things. First, it makes all the errors positive. And second, it heavily penalizes the bigger errors. A big mistake gets counted way more than a few small ones.
Okay, so we get the idea of minimizing error. How does that translate into actual math? Well, let's look at the simple equation that describes the line itself.
You'll probably recognize this from basic algebra. It's just the equation for a line. In machine learning, we write it as y prime equals b plus w1 times x1. This equation is the model.
Let's break it down really quick. Y prime is our prediction. X1 is our input feature, like the size of a house. W1 is the weight, which is just the slope of the line. It tells us how much the prediction changes when the feature changes. And B is the bias, which is our y-intercept, a baseline value. So learning the model just means finding the best possible numbers for B and W1. To guide this search, we need a single number that tells us how badly the model is doing. That's the cost function. For linear regression, we typically use mean squared error, or MSE. It's just the average of all those squared residuals we talked about. The entire goal of training is just to find the B and W that make this MSE value as small as it can possibly be.
So how does the machine actually find those perfect values? It doesn't just guess randomly. It uses a powerful search algorithm called gradient descent.
The best analogy for gradient descent is to imagine a giant U-shaped valley. The lowest point at the bottom of the valley is where the error is at its absolute minimum. We start by placing ourselves at a random spot on the side of the valley. Then, we look around, find the steepest downhill direction, and take one step. We repeat that over and over, find the steepest way down, take a step, until we finally settle at the very bottom. The coordinates of that final spot, those are the best values for our model's bias and weight.
Okay, enough theory. Let's connect this to how you'd actually use it in practice.
Linear regression is a true workhorse algorithm. You see it everywhere. It's used in real estate to predict house prices, in marketing to forecast sales based on ad spending, in finance to model economic variables, and even in agriculture to estimate crop yields from things like rainfall.
Now, we've been focusing on simple linear regression, which uses only one input feature.
But the idea scales up perfectly. When you use multiple features, like a house's size, age, and number of bedrooms, it just becomes multiple linear regression. The equation simply expands to include a new weight for each new feature.
So, as a practitioner, why should you care about this seemingly basic algorithm? Well, because it's fast, it's efficient, and it is incredibly easy to interpret. You can look at the weights and understand exactly what's driving the predictions. And most importantly, it's the conceptual foundation for many, many more advanced models.
So, to wrap it all up in one sentence, linear regression finds the best fit straight line through your data to predict an outcome.
And the key takeaway to remember is this: even the most complex, sophisticated deep learning models are, at their very core, doing the same thing. They're just optimizing parameters to minimize a cost function. It all comes back to the simple, powerful idea of finding a model that minimizes its own error.